Okay, today we're going to talk about the molecular-empirical formula relationship. Now, we've talked about empirical formulas before, but there's going to be some review on what that means. So let's look at this assignment, and we'll use this Google Slides assignment. This first part is something that we've done before, but it's a good refresher. That was 2 weeks ago. Okay, so first of all, what is an empirical formula? And so let's take a look at what that means. It represents the simplest integer ratio in which atoms combine to form a compound. So let's take a look at some examples. These are empirical formulas. The first one is ionic and the second one is molecular. Ionic because it's a metal and a nonmetal. Second one is because it's two nonmetals. A non-example would be these right here, and any non-example of an empirical formula will be a molecular formula. It will not be ionic. Ionic compounds are always empirical. And to reduce a molecular formula into its empirical formula, you find the common factor and divide by that. And so you can see for these questions right here, then you would use or answer them on the Google Doc right here. All right, so that again, that was review. We've done that before. All right, so now let's look at a little more in depth of the relationship between an empirical formula and its molecular formula. Okay, so let's say we have a molecular formula like this. If we calculate the formula mass of hydrazine, the formula mass, we would get something like this. Now you're going to see it in AMUs and it's the same number as if we were to find the gram formula mass in grams per mole. This is just adding up the atomic number on the reference tables. Not the atomic number, atomic mass, sorry. So we see that it's 30 AMUs, or grams per mole. Now, what if we were to find out the empirical formula of hydrazine? It would be this, and what would be the mass of that? Well, we would have just one of each atom, and we would see that its mass was 15 AMU, or 15 grams per mole. Well, this number 15 compared to the molecular formula, which was 30, is greater, the molecular formula is greater by a factor of 2, right? Which we would expect, since to reduce the molecular formula to the empirical formula, we can divide each subscript by 2. And we see this relationship between them. So knowing that, if we know the molecular formula mass, we can find out the empirical formula. We can find out the molecular formula. That's where that 2 comes from. So let's say we have a compound that has a formula mass of 180 grams per mole, or AMU, and its empirical formula is CH2O. What is the molecular formula? We know the molecular formula will have numbers greater than 1, 2, 1. How many more times greater? Well, let's find the mass of this empirical formula. And we see that take 1 of carbon, 2 of hydrogen, 1 of oxygen. We find that it's 30. How many more times is 180 compared to 30? find that it's 6. So that means to find the molecular formula, we multiply each subscript in the empirical formula by 6. And now we know what our molecular formula is. Because both the mass and the number of each atoms is related by that factor of 6. So now you should be able to finish the rest of that Google Slides.